Welcome to a Rice University podcast. For more information about us, please visit our website at www.rice.edu.
Good afternoon, everybody. I'd like to extend a warm welcome to you all to this second lecture in our series this year. My name is Susan McIntosh, and I'm the director of Scientia. Our theme of networks this year brings together speakers from a variety of disciplines who use network models to elucidate the properties of a variety of complex systems. Our first exploration into networks began with Michael Lindsay's work on elite social networks and the flow of power. We continue today with another look at human networks of contact and sociality, but this time focused on the flow of viruses. The H1N1 virus has, of course, been afflicting our campus for several weeks. I just traveled this weekend to another smaller campus, and that campus has seen no cases of H1N1 yet. I mean, they almost certainly will. And predicting the spread of viruses using network models is one of the specialties of our speaker today. We're extremely fortunate to have Lauren Ancel Meyers with us to share her cutting-edge insights. Lauren Ancel Meyers received her BA degree in mathematics and philosophy from Harvard in 1996 and her PhD from the Department of Biological Sciences at Stanford University in 2000. After completing a postdoctoral fellowship supported by the National Science Foundation, she joined the faculty of integrative biology at the University of Texas at Austin in 2003, where she was promoted to associate professor with tenure in just 3 years and now serves as the associate director of the new campus-wide division for statistics and scientific computation. She's also been an active member of the external faculty of the Santa Fe Institute since 2003. Her research lies at the interface of evolutionary biology and epidemiology. She has developed new network-based mathematical methods to study the interplay between disease transmission dynamics, human behavior, and the evolution of pathogens, including those responsible for epidemic meningitis, influenza, walking pneumonia, and SARS. Her research has been funded by 5 major research grants and 7 collaborative grants from the National Institutes of Health, the National Science Foundation, the Canadian Institutes of Health Research, and the James S. McDonald Foundation. The Wall Street Journal, Newsweek, the BBC, and other news sources have highlighted her work, and a number of government agencies have sought her expertise, including the Centers for Disease Control and Prevention, the British Columbia Center for Disease Control, which I understand is in anticipation of the 2010 Olympics at Vancouver, the U.S. National Intelligence Council, Los Alamos National Labs, and Lawrence Livermore National Labs. She has published 36 papers on topics in mathematical epidemiology, evolutionary biology, and statistics in a wide variety of journals, and she currently serves or has served as an associate editor of the journals Epidemics, Evolution, Public Library of Science Computational Biology, the Journal of Molecular Evolution, and Interdisciplinary Perspectives on Infectious Diseases. In 2004, the MIT Technology Review named Lauren as one of the top 100 global innovators under 35. So it is with particular pleasure that I ask you to join me in welcoming Lauren Ancel Meyers to the podium.
Thank you very much, Susan. I'm just going to get the microphone set up and then I'll begin. Okay. Can you hear me? Yeah. Okay. Well, thank you so much. It's really a delight to be here. This is my second visit to Rice in the last 12 months, and it's been incredibly enjoyable. It was a unique opportunity to have lunch at a table that was filled with a philosopher, an archaeologist, a chemist, a structural biologist. Who am I missing? I don't know, but it was a really uniquely diverse and wonderful lunch today, and really thank you so much for having me here. So I'm going to, based on my lunch conversation, I imagine that this is a pretty diverse audience, And I think, at least in part, I'm going to be talking about a topic that may unite us all. At least we've all been thinking about it. I hope we aren't all afflicted by it. But that topic, as Susan mentioned, is H1N1 flu. And you've heard a lot about it in the last few months, and I'm going to tell you a little bit more generally about flu and about H1N1, just so we're all on the same page, and you and I can share with you what I think are some of the most interesting aspects of the flu virus in epidemiology. And then I'm going to move on and talk a little bit about traditional approaches to modeling the spread of infectious diseases that have been with us really since the early 20th century. And then move on to the theme of this year's lecture series, and that is how we are using network models to help better understand the spread of diseases and forecast the spread of diseases, as well as develop more effective intervention strategies using network models. And I'm specifically going to talk about how recently we've used network models to address questions like how quickly is H1N1 spreading, which age groups are at risk now and in the future, and who should be vaccinated now that we have vaccines starting to become available across the United States. And then finally, I'm going to talk about another recent tool in our toolkit of epidemiological modeling, and that's some very nifty optimization techniques that come to us from operations research, and how we've recently applied those to thinking about how best to deploy the strategic national stockpile of antivirals in the United States. So let's start with some flu basics. So flu, as many of you may now know or already knew, is a disease that causes seasonal epidemics. So every year we have huge epidemics in the United States, and typically it leads to hospitalization of hundreds of thousands of people and deaths of often 30 to 40,000 people. This is a graph showing the rate of deaths due to flu or flu-like illness throughout the 20th century. This happens to be from data from the state of Maine. And what you can see is that pretty much we have sort of low levels of death due to flu with this very pronounced spike. I'll tell you about that spike in just a second. But what happens is year after year we see strains that look slightly different from the strain the year before. And that is because the virus that causes flu is continually evolving. And that is the reason that every year we have to come up with a new flu vaccine cocktail. And that you need a new flu vaccine if you want to be protected in 1 year. Even if you've been vaccinated the year before. So what is the spike about? Well, occasionally we get a brand new strain of flu introduced into the human population that looks nothing like or very little like the strains that have been circulating in recent years. And the way this usually occurs is the following. There are always many strains of flu circulating in wild waterfowl populations, and these are mostly strains that have never been introduced into humans or certainly never caused sustained outbreaks in humans. Occasionally these strains get introduced into domesticated animal populations like poultry populations or pig farms. And if we're unlucky, it actually causes disease and outbreaks in these populations. And if we're really unlucky, it then gets introduced into the human population and gains the ability to spread from human to human and causes a large outbreak. When this occurs, when we get a brand new strain introduced in the human population, we call it a pandemic. And we had 3 pandemics in the 20th century, and you're probably mostly aware of at least one of these, and this is the one that caused this spike here. This is the infamous 1918 Spanish flu pandemic. It was also caused by a strain that's numbered H1N1, although it's a different strain than the H1N1 that's circulating today. So it turned out to be a much more virulent strain than the strain we see circulating today. So this strain popped up in 1918. It caused a devastating pandemic. It probably, in that season, killed up to 100 million people around the globe. And after that season, it returned in a less virulent form. And year after year, we had seasonal outbreaks caused by the descendant or descendants of that particular strain that appeared in 1918. The second pandemic of the 20th century occurred in 1957. A brand new strain, again, appeared in the human population and caused a large epidemic. It's strain number H2N2. The H and the N refer to proteins in the flu molecule and the numbers refer to the specific version of the protein that is in that flu virus. And when this appeared in 1957, it caused a large epidemic, large pandemic, and it completely displaced the descendants of H1N1. So after 1957, we never saw any more H1N1, and what we saw season after season for several years were descendants of this new strain, H2N2. In 1968, we had our third pandemic of the 20th century. It was numbered H3N2, called the Hong Kong flu, and just like the previous pandemic, it displaced all of the currently circulating strains. So then we entered a period where we only saw H3N2 strains causing seasonal epidemics. Okay. Since 1968, there's been a lot of activity with flu. In 1976, we had a swine flu scare that many of you who are old enough to remember. And in this particular outbreak, there were a few hundred people who were infected in Fort Dix, a military complex in New Jersey. And it never actually spread beyond that military base. So nobody in the general community got it, nobody outside of New Jersey got it. Nonetheless, Gerald Ford decided to institute a universal vaccination campaign. They tried to vaccinate everybody in the United States against swine flu, even though it was clear by then that it really hadn't spread beyond Fort Dix. And by the time they had vaccinated about 40 million people, there appeared to be a problem with the vaccine in that several hundred people appeared to have developed an immunological disease called Guillain-Barré syndrome, and they believe it was because of the vaccine. That's never been conclusively proven. Nonetheless, there was enough of a scare that people stopped getting vaccinated at that point. And it's important to, I think, mention this because a number of people today are unwilling to get the current H1N1 vaccine because of fear that's still residual from this experience in 1976, even though it was never conclusively proven that the vaccine caused the problem and that the way they make vaccines today is very different than the way they were making vaccines back then. But that appeared and then disappeared. It was also an H1N1 strain, though different from today's H1N1 and different from this H1N1. So it disappeared without doing much damage. And then in 1977, we had a reintroduction of H1N1 that was closely related to the H1N1 that was circulating prior to 1957. It was called the Russian flu, although it's widely believed that this H1N1 was actually a lab escapee from a lab somewhere in China near the Russian border. So this was something that was kept in someone's lab, somehow got out into the general public and started causing disease. And since then, we've actually seen a combination of H1N1 and H3N2 causing our seasonal epidemics. Why this release didn't completely displace the current strain like the previous pandemics did, we don't know. It's a really interesting and unanswered question. But that's what we've seen since then. Around 1977, we started becoming aware of a new strain called H5N1. This is what's been called avian or bird flu. You might probably have heard about it in the news over the last 5 years. And it's a strain that's caused large, devastating outbreaks in poultry populations, so in chicken farms. And occasionally, individual humans have gotten infected with this strain if they come in close contact with the sick birds. And when they become infected, they get very serious disease. In fact, they believe that over half the people who become infected with H5N1 have actually died, which is a very high case fatality rate, a very high mortality rate, much, much higher even than seen in 1918. And the fear has been that that strain would evolve the ability to spread from person to person and cause a devastating and very large pandemic. Fortunately, that hasn't happened. We continue to see isolated cases, but we haven't seen sustained human-to-human transmission. It's still a concern. It has sort of left the media spotlight recently because we've been more concerned with the pandemic we're actually facing right now, which is fortunately much milder in terms of the severity of disease it causes. Which brings us to today's new strain, 2009 novel H1N1, which we believed emerged originally in Mexico, probably sometime in March and April of 2009, and since has become a global pandemic causing millions of cases around the globe. So where are we? Oh, and the one thing I was going to mention is we don't know what's going to happen in the next couple months. Are we going to continue to see this new H1N1 exclusively? And see these prior strains that have been causing our seasonal epidemics disappear? Or will we see a combination of the new H1N1, the old H1N1, and H3N2 this season and in seasons to come? We just don't know. Okay, so where are we today in the United States? Well, it is very difficult to estimate how many people have been infected because many infections are probably mild or even almost asymptomatic. And even if they're serious, you may not go to your doctor. It may never get reported. So it's really hard to know how many people have gotten infected. By my calculations, we're talking about already tens of millions based on the number of reported cases and what we know about flu. There have been reported by the CDC almost 22,000 hospitalizations that are likely due to H1N1 and almost 2,500 deaths in the United States due to H1N1. This is what we call epidemic curve for H1N1 looks like. So let me orient you here. We're going along a year here. Starting at basically, what would this be? The second week of October, there's the new year, January, February, March, and now going to the end of September, beginning of October. What you see here in green and blue are flu curves from previous years. So this is basically how many people have been infected at different times of year by the flu during previous seasonal outbreaks. And what you see in the 2006-07 season and the 2007-08 season is that school starts about now, and you start to see a ramping up of cases towards the end of December. Then kids go on holiday for winter break. You get a decrease in the number of cases. Kids come back to school. And then you see the real surge in your typical seasonal flu outbreak. And then it comes back down in the late winter, and then it disappears in the summer. The red line is showing you what the data from this year. So last winter we had sort of a typical outbreak, a surge in December, comes back, really peaks in, I guess that's February, March-ish, and then it looks like it's going away for the summer, and then suddenly H1N1 appears, and we get sort of sustained transmission at low levels throughout the summer, and then a huge surge in cases basically when kids went back to school this fall. I'm not sure what this little dip is about. If you look at Google Trends data instead of CDC data, which is data based on how many people are querying information about flu symptoms, flu concerns, you actually see almost an identical pattern here, except that this is smoothed out and you don't see this little dip. So I'm not sure if this dip is even real. We should look to Google. Anyways, here we are. This is 2 weeks ago. The most recent data point has actually come out, and it's way up here. It's right about there from last week. So we're still in the midst of the crescendo of this current wave of flu transmission, and we don't know how close we are to the peak. There's good reason to expect that this peak may be significantly higher than the peaks we've seen for seasonal flu in previous years, because we're dealing with a population that's probably almost 100% susceptible. In previous years, when you have normal seasonal flu, some part of your population got vaccinated, some part of your population got sick the year before and so has some immunity to the current strain. But now we're dealing with very, very few people have gotten vaccinated in the last week, but pretty much almost no one's been vaccinated and almost everybody's vulnerable. So this could surge quite a bit more before peaking. But let's just say we really are within a couple weeks of this peaking and that we sort of peak and then come back down, maybe let's say in the first week of November or late October. Then the question is, are we in the clear? Did we just we dealt with our flu season in the fall and now we can rest easy? We don't have to worry about what typically happens in December and January and February because we've taken care of it and now we have immunity? And the answer to this question is that we shouldn't assume that we are in the clear. And why is that? Well, there's a number of reasons. One is if we look back to prior pandemics, we see a very unusual pattern. Okay, so if we look back to 1918 flu, which was much more severe, this killed people at a much higher rate than H1N1. So I just want to mention that so you don't think we're in exact same situation. We did see something that looked quite similar to what's going on now. We had a wave in the summer, sort of quieted down, and then a big fall wave around the same time we're having a big fall wave now, and then something that was basically we've almost never seen since or before, and that is a third wave that occurred in the late winter. Why this happened, we don't know, but it happened. It could be that because the virus evolved a little bit in the intervening period, and so some people who were infected then were no longer immune. It could be that it reached another portion of the population. It's unknown. If we look in 1957, which was the second pandemic I mentioned, we saw a similar pattern. There was no summer wave, but we had the fall wave that took place about this time of year. It almost went away, and then we saw a second wave in the winter months in February, March. All right? So based on what's happened in previous pandemics, we may not be dealing with one wave. We may be dealing with 2 or more waves this year. And even if we're fortunate and we don't see this H1N1 return for a second wave, we may actually face other strains of flu. So this is a map showing the lab results for flu tests from around the globe. This is fairly up to date from a couple weeks ago, and the parts of the pie that are in turquoise indicate the fraction of lab reports that came back positive for H1N1, and the fraction that's in purple shows the fraction of lab reports that came back positive for something that's not H1N1. And the majority of these are subtypes that are typical seasonal flu strains. So for example, in Australia, this little wedge here were outbreaks of H3N2, our normal seasonal strain, and there's some concern that this Australian strain may actually cause a worldwide epidemic of sort of normal seasonal flu. Unfortunately, this particular strain of H3N2 didn't happen to make it to our seasonal flu vaccine. So those of you who did get your regular flu vaccine, if this one comes back, if this is the one to cause a worldwide epidemic, you're not going to be protected by the vaccine, although you would be protected by infection in previous years. So we may not be out of the woods. It's a good reason for everybody to go ahead and get their H1N1 vaccine and their seasonal flu vaccine, because we don't know what's going to happen in the coming months. Okay, so what has the public health infrastructure been trying to do since we realized that H1N1 was going to be a major global threat in April and May? Well, they've been working hard to develop and deploy effective H1N1 specific vaccines, and we're in the early stages of distribution in the US of those vaccines. We've also, to some extent, used antiviral medications for prophylaxis and treatment. So that prophylaxis just means you give people the medicine to prevent them from becoming infected, and treatment means you treat somebody and it hopefully will reduce their symptoms and make them recover more quickly. And then all sorts of non-pharmaceutical interventions taken from an individual level to a larger governmental level, things from you deciding to wash your hands more or not go to some social event or keeping your distance or covering your mouth, to school closures or public closures of other places where people gather. Okay, so where do we come in? I'm a mathematical modeler. There's others like me who are interested in using models to try to understand and forecast the spread of disease. Well, in my particular group, we were awarded an NIH grant very recently in June 2009. It's a 5-year grant, and the focus of the grant is to study the impact of individual perceptions and behavior on the spread of flu and the effectiveness of control strategies. Okay. Well, it turned out there was fine print in the request for proposals that we responded to in asking for this money. And the fine print said, in the event of an attack or the emergence of an infectious disease, basically NIH wants you to drop everything you're doing and help us and develop some models and help us figure out what's going on and respond. Okay? So on April 26th, even before we got the money, we got the call. And it's not just our group. I'm part of a collaborative project with a woman named Allison Galvani at Yale, but there are a number of other groups at Harvard and University of Washington and University of Pittsburgh that are also funded by this program that have all been working collaboratively and independently with public health agencies and with NIH to try to contribute to effective decision making. So we've been working with the CDC, BARDA, which is the agency in Health and Human Services that's actually responsible for purchasing and deploying the vaccines and the antivirals. Locally, Texas Department of State Health Services, British Columbia, and other public health agencies. Okay, so I'm going to take a step back. Before I tell you what exactly we've been doing, I'm going to tell you a little bit about mathematical modeling in this field of infectious disease epidemiology. So the question is, how can math and statistics actually help us to address these public health problems? And generally speaking, the way that it comes in, or at least in one way, is that in infectious disease epidemiology, you can't really do the kind of controlled experiments a scientist would like to do. If you want to know how effective a particular vaccine strategy is going to be, you can't go out and intentionally infect two populations and vaccinate one in one way and one the other way to see how it's going to work. And it's very rare that you have retrospective data that's kind of clean enough to allow you to make these kinds of studies. And so what math and statistics sometimes allow us to do is to do these kinds of experiments virtually, to kind of, in a virtual world, imagine disease spreading through a population and evaluate what the efficacies are going to be of different strategies to combat the disease. So although the history of mathematical epidemiology goes back centuries, I'm going to start at the beginning of the 20th century and talk about the dominant framework for modeling the spread of infectious disease. And it's still used today by the vast majority of mathematical modelers. It's a powerful framework called compartmental modeling. And the basic idea is you subdivide a population into different groups based on the history of exposure to disease. Okay, so in this case, we're going to break a group into population into three groups: individuals who are currently susceptible, so they haven't been infected yet; individuals who are currently infected; individuals who are recovered. And you can imagine when a disease spreads through a population, it starts susceptible. You get someone who's sick. They move to the infected compartment, they expose some people who become infected, and then at some rate those infected people recover, and so on and so forth. And you can imagine disease kind of moving through these through these subgroups, and you can write systems of equations to describe the changing numbers of individuals in each of these groups as disease spreads through the population. Okay? In building these models, we make one very important assumption. It's something we call the mass action assumption. That term is borrowed from chemistry. In chemistry, the mass action law is that the rate of a chemical reaction is going to be proportional to the product of how much of each of the inputs you have into the reaction. So in this case, something very similar is going on. We're going to assume that the rate at which new people become infected in a population is related to how many susceptible individuals there are in the population times the number of infected individuals in the population. Okay? And so we make this assumption because it makes the math work out nicely, and it may be reasonable in some situations. So essentially, what is this saying? We're assuming that everybody has essentially the same contact rate, and we're assuming that essentially we have one big mixed population, so that when someone goes out and bumps into someone that they could spread or catch disease from, they're just picking someone at the random from the population to bump into. Okay? And again, these assumptions can be reasonable in some situations, but they're also unrealistic in others. Okay. So one very important quantity in epidemiology, and one quantity we really focus on when making these kinds of models, is something called the reproduction number. And it basically tells us how quickly a disease is going to spread in a population. All right, so what is this number? Well, it's a ratio between the infection rate, so how quickly we're getting new infected individuals in the population, which is governed by that term, beta times SI, divided by how quickly people are leaving the infected compartment, either because they're recovering from the disease or they're dying. Okay? So the ratio of these two things, the infection rate divided by the mortality plus the recovery rate, tells us something about how quickly this group is going to grow, how quickly we're going to get new red dots in our population. Okay? We typically use the symbol R sub 0. Sometimes it's just referred to as R naught, to denote the reproduction number. And in symbols, what this is equal to is beta S, this is sort of the rate of transmission times how many susceptibles we have, divided by the recovery rate plus the death rate. Okay? So this is telling us how quickly people are entering that infected group, and this is telling us how quickly people are leaving that infected group. Okay? And so we can use this kind of model and this kind of framework for addressing questions like, when will an outbreak become an epidemic? When will an outbreak cause infections of large numbers of people in your population? Well, we can look at this ratio. If the rate at which new people are becoming infected outpaces the rate at which people are either dying or recovering, then that ratio is going to be greater than 1. And these models predict that you're going to get large-scale epidemics with some probability in your population. If instead we have the reverse relationship and the rate of infections, the transmission rate, is lower than the rate at which people are either dying or recovering from the disease, then this ratio or this number will be less than 1, and we predict that the epidemic will fizzle out before infecting a sizable fraction of the population. Okay? So one very important concept in epidemiology is a concept known as herd immunity. It's the idea that you can protect part of the population directly and indirectly protect the whole population, thereby indirectly protect the whole population. So specifically, you might vaccinate part of a herd of like sheep or something against some disease, and maybe you just vaccinate 50 or 60 or 70%, but you prevent an epidemic altogether, and you thereby indirectly protect the remaining 30% or however many. Okay? So one of the things that, one of the things we can use this equation to think about is how can we prevent an epidemic? So suppose, well, first of all, in terms of R0, what does it mean to prevent an epidemic? What do we want R0 to do? Any ideas? We want it to get less than 1, okay? So what can we do if we have a disease where R0 is greater than 1? What kind of things can we do as a public health effort to bring R0 less than 1 so we make an epidemic impossible in a population, okay? Well, we can think about each of these different symbols, right? There's sort of 4 different symbols we can play with. Each one, moving in a certain way, will help us reduce R0. So the first thing we can do is we can reduce beta, which is in the numerator here. So what could we do to reduce beta? Beta is sort of the product of how often you come in contact with people and the likelihood of transmission when you do have a contact with someone. So what could we do to reduce beta? Stay at home, right? So stay at home, exactly. So you reduce your contacts. Or maybe you could wear a face mask, so if you do go out and you interact with someone, you make it less likely that you actually transmit disease, or wash your hands more. So you can reduce your contacts, or you can do something to prevent transmission during a contact, right? So we could also increase nu. Nu is the recovery rate. So how might we do that for flu, for example? Tamiflu, exactly. So Tamiflu, if you take it early enough, should reduce the time during which you're infectious from, what could be up to 2 weeks down to maybe 2 or 3 or 4 days. Exactly. Now, I'm not advocating this, increasing delta. Delta is the death rate, and certainly we never think about this for humans, but this is actually a very viable and often used control strategy for livestock, right? If you have a sick herd, you might actually start killing off fractions of your herd that are infected. And certainly this is actually a very commonly used strategy for H5N1 in bird populations. They cull entire chicken farms, basically, to prevent the spread of H5N1. But it's not one we think about in human public health. And then finally, the one that I'll focus a little bit more on is we can reduce S. So what do we do? How do we reduce S? We vaccinate, right? The S is the size of the susceptible population, and the more people we vaccinate, the smaller we make our susceptible population, okay? And a lot of the work that was done throughout the 20th century with these compartmental models addressed the question of how many people do we need to vaccinate in order to eradicate a particular disease. And the calculations were based on different versions of the models that I showed you, and based on estimates for the reproduction number of the disease. So I just mentioned something. So another way of thinking of the reproduction number, instead of this kind of abstract quantity about how quickly that group is growing, another way to think about this is the reproduction number is essentially the following. If you have a totally naive population and you have a single infected person enter that population, it's the expected number of secondary infections that that person will cause. So in other words, it's the expected number of people they will infect. So a reproduction number of, let's say, 5 to 18 means that on average you expect, at least early in an outbreak, individuals to infect 5 to 18 other individuals. Based on one of those estimates in that range, there have been models that suggest that in order to eradicate measles, you have to vaccinate 90 to 95% of your population. For chickenpox, some of the published models suggest you have to vaccinate 85 to 90%. For polio, which has a lower reproduction number, you don't have to vaccinate quite as much of your population in order to eradicate the disease. Smallpox, other estimates. And then I'm going to get back to estimates for the reproduction number for H1N1 in just a minute. And the reason I'm not going to tell you what the estimates are now is because it turns out we need a little bit more mathematical sort of equipment to be able to address the reproduction number for H1N1. These compartmental models don't quite capture the complexity of the situation. So we'll get back to that in just a minute after I tell you something about networks. Okay, so why am I going to go on to tell you about networks? Well, I want to highlight that this modeling approach, while it's been quite effective, and you can certainly make much more complex versions of this, sometimes the simplifying assumptions are just too simple or just don't capture important features of your population. So recall, I said that in building these models, we assume that everybody has the same contact rate, and you have one big mixed population. And often that's not going to be true. There's a lot of heterogeneity between people and through time in terms of how many contacts people have and their opportunities for transmission of disease. Some people have lots and lots of daily contacts by virtue of their work environment, their way they commute to work, their school environment, or their recreational activities. And other people will have far fewer contacts on a typical day because of their lifestyle. And there's not only this kind of heterogeneity within a population, but between populations, between the weekdays and the weekends, etc. And so we and others have developed other mathematical approaches that allow us to capture some of this important heterogeneity. And one way to do it is through network modeling. So instead of lumping everyone together and assuming they're homogeneous and everyone comes into contact with everyone else, we can explicitly represent patterns of contacts through a network model. So here, these circles represent individuals again, the lines represent contacts that could potentially lead to disease transmission, and the colors again represent the same thing here as susceptible, infected, and recovered. And you can see at this point in time, this individual is much less vulnerable right now. They only have one contact, and he's currently susceptible than, for example, I don't know, this individual here who has two contacts that were recently infected and has a third contact, or two more contacts along which they could become infected. Okay, so let me define some terms which you may have heard in the last lecture on networks, but I'll remind you. So we typically call these circles in the network either nodes or vertices, and in epidemiology, we use them to represent people or animals or groups of people. I think this should work. Okay, and the lines represent what we call edges, and those are contacts between individuals or groups or locations that can lead to the transmission of disease. And then an important quantity we often talk about is the degree of a node, and that's just simply how many contacts does an individual have or how many edges are coming out of that node. And so in this network, this individual has one contact, this individual has 4 edges or a degree of 4, degree of 3, a degree of 6, etc. And we often want to know what is the distribution of degrees across the whole network. What fraction of my network, what fraction of individuals in my population just have one contact, have 2 contacts, 3 contacts, etc. And we can summarize that information in what we call a degree distribution. And here I've represented the degree distribution in a histogram. Okay. So network modeling in epidemiology, I usually think of as sort of a 3-step enterprise. And the first step, and often the most difficult step, is to try to build a realistic contact network model. So what are the patterns of contact out there in a human population or an animal population that actually lead to the transmission of diseases? And it's often very difficult to get reliable data about that. And then the second step is to develop or apply mathematical and computational tools to predict how disease will spread through the network. And finally, we use some of those tools to address specific public health or ecological questions about disease transmission and control. Okay, and I'm going to go through each of these steps very briefly with some examples. So how might we build a realistic contact network model? Well, we've done this on multiple scales in my own group, and others have worked on this as well. So this is a picture of a United States level network where the nodes represent the 100 largest cities in the United States. The sizes of those nodes represent how many people live in each of those cities, and the weights of the edges between the nodes represent how many people travel between those 2 cities, either by air or car or rail. At one level lower, we've built models of contact patterns within an urban setting. This particular model that I've cartooned here is a model we developed of contact patterns in the city of Vancouver based on detailed census and school district and hospital bed and other types of data. And we connect people based on who they live in the same household with, who they go to work with, who they go to school with when they visit the hospitals. And we even go down to smaller scales. This is a cartoon of a network we built based on detailed information from a particular psychiatric institution that experienced an outbreak of walking pneumonia in Evansville, Indiana. And in this particular case, we had very detailed information about where the different residents lived, who they interacted with, and who the different caregivers were, and which groups they interacted with. And this particular network, I would call a tripartite network. You don't just see one circle type. You see 3 kinds of nodes. You see caregiver nodes, you see ward nodes, which are locations, and you also see patient nodes, which are these blue circles there. And so sometimes the kind of network representation you use may involve many different kinds of nodes and many different kinds of edges. Okay, so those are just some very brief examples of the scales and the kinds of data we use to build contact network models. Then once we have a decent network model in hand, we want to predict how disease is going to spread through the network. And to do this, we largely have borrowed and adapted methods from an area of statistical physics called percolation theory. And the idea is we introduce disease somewhere in the network, and we want to know, based on the contact patterns in that network, where disease is going to spread, what parts of the network are going to become infected, and at what points in time. And so, like I said, this is some of these approaches were originally developed over 50 years ago in this area of physics. That was originally developed to address problems like how would a fluid flow through some medium where you have a bunch of channels that can either be opened or closed, and you want to know, based on the configuration of those channels, whether or not the liquid would percolate or move through the material, what parts of the material would get wet. And so it's an analogous process here, but our connections in this case are between individuals in a population, and our fluid is the disease itself. And the idea to adapt some of these methods to mathematical epidemiology was actually originally suggested back in 1983 by a guy named Peter Grasberger, but never really took off. But then in 2002, Mark Newman, one of my collaborators and a real pioneer in the field of network modeling in multiple fields, a guy named Mark Newman at University of Michigan, sort of reintroduced the idea and further formalized it. And since then, this field and this approach has really taken off. Okay. So I'm not going to talk too much about how we do our calculations. I will just mention what goes into our calculations, and it's basically two ingredients. The two things we take into our calculation are something about the structure of the network, and what we usually look at is the degree distribution. So recall, that's just what fraction of our network has 1 contact, 2 contact, 3 contact. It summarizes some of the important features, though not all of the features of the network, and it tells us some good information about how disease will spread. And then the second ingredient tells us something more, not about the structure of the population, but about the pathogen that's spreading through the population. It's something we call transmissibility, and it's basically the probability that when you're infected, you're going to spread disease to somebody on the opposite side of an edge, okay? And so that can vary from edge to edge, and we take into account that information when making our calculations. So what can we calculate? Well, we can calculate something like, can a disease spark an epidemic? Is this disease contagious enough to actually start spreading widely in a population? Presumably, strains of flu are introduced all the time from bird populations into domesticated animal populations, and maybe even domesticated animal populations to humans, but they rarely take off into a pandemic. So what does it take for a disease to actually be able to cause a large pandemic and become our next major strain? We can make predictions about how the diseases are going to spread, the dynamics of disease, through populations that are complex, that where you can't just assume that everybody is that you have homogeneous contact patterns and that everybody's contacting everyone. We can make predictions about who in a population is going to get sick at different points in time, and does it matter who gets sick first? So the predictions may depend on where the disease first emerged. Was it Mexico City? Was it La Gloria region in Mexico? Was it New York City? Was it some small town in Texas? The pace and the spread of the disease will depend very much on where things start. And the bottom line from a lot of the early studies using this approach is that network structure really matters. As you make realistic contact network models, you see that different populations will experience very different outbreaks, even if it's the exact same disease spreading through the population, just because of the contact patterns in that population. And so it's not always going to be appropriate to make the simplifying assumptions we've made in the past for the mass action models. Okay, so let's get back to this question. So what have these kind of calculations allowed us to do to help understand what's going on with H1N1? Well, remember I told you something about all these reproduction numbers, and then we got to H1N1 this spring, and all of the mathematical modelers and epidemiologists and statisticians were scrambling to make sense of the early data coming out of Mexico City and some of the data coming out of San Diego and New York, where we had the first outbreaks in the US. This is what the early data looked like out of Mexico City. So this is the early data of probable cases from the Mexico City Public Health Department. And what we wanted to do was estimate the reproductive number. So how quickly was H1N1 spreading in its early days? And essentially that's like estimating how quickly these numbers are increasing. Okay, so we're sort of fitting a line here almost. But it turns out, and we can do this using compartmental models, but it turned out there were a lot of weird sociological or anomalous sociological things happening in Mexico City at the time that were critical to consider in trying to estimate how fast this disease was spreading. Because what we wanted was a robust estimate that was going to tell us when H1N1 got to Houston or Austin, how fast was it going to spread here? Okay, and so it turned out things were kind of strange in Mexico City at the time. First of all, when H1N1 was just beginning to take off in Mexico City, schools entered the 2-week vacation period, the Holy Week period. Schools were shut down, a lot of workplaces were shut down, a lot of people went out of Mexico City for vacations. And so if this had been kind of normal sociological conditions during the end of the school year, this might have taken off much more quickly than we actually saw, because the city shut down and contact patterns were reduced quite a bit in the city during that period. In addition, towards the end of the Holy Week period, when things really started taking off, public health became aware that there was possibly a problem, and there was increased surveillance. So cases that would not have been reported before this point in time were now much more likely to be reported. So we had suddenly a difference in reporting rates. And then on top of that, we had a declaration of a public health emergency, or awareness in the general public, happened somewhere in here a couple days after that. And that led to not only detection of more cases, but also this phenomenon we call the worried ill or the worried well, people who don't actually have H1N1, but who have symptoms, maybe mild symptoms, respiratory symptoms, going to the hospitals, going to the doctor, worried that they have this new plague that they've heard about in the news. And so this also really increased the rate of both accurate reporting and misreporting. And so we were trying to make estimates as quickly as possible without waiting for confirmation of these cases. And so taking all these things into account, changes in contact patterns, changes in misreporting in both directions, took a lot of really kind of innovative statistical work, and we definitely considered network structure. And I'm not going to go into the details, and there were actually a number of different really excellent mathematicians and statisticians from around the world, from Canada, from Mexico, from the United States, working on this problem. But I'll just tell you what we found. What we found from this data, and since from more recent data from the US and the rest of the globe, is that H1N1 is spreading about as fast as we expect for almost any, as we've seen in the past and we expect for almost any strain of flu. Okay, so it's not that atypical. It looks pretty much like we've seen for newly emergent pandemic strains in the past, and it's pretty close to what we see for epidemic flu season after season. And so what is the estimate? Well, the early estimates in Mexico City was about 1.4. So right, this is the reproduction number. That means each case is infecting somewhere between 1 and 2 new cases on average. But there's quite a range of error, so they might have been as low as 1, as high as 3. Since then, with more data, we're pretty confident that the reproductive rate number is probably somewhere between 1.2 and 1.6. So that was one of the first things we addressed. The second thing we tried to figure out, and we used network models to help us understand this, is try to forecast who's going to be, what parts of our populations demographically are going to be infected with H1N1. Okay? And we saw that there were, although in Mexico City there were a lot of adults becoming infected, what we saw in the US during the first stages of the outbreak were lots of kids getting infected and not so many adults. And when we looked back to past pandemic years and we dug through the data, we found that for most prior past pandemics, and you also see this for most seasonal epidemics as well, the attack rates, the infection rates in school-age children typically exceed the attack rates in adults quite a bit. So that the blue bars here are showing how the fraction of kids getting infected compared to the fraction of adults getting infected for 1918, for 1957. It's a little bit closer in 1968, and then the early data from H1N1 suggests the same thing. So this suggested to us, and not surprisingly, and I think it's what public health expected, that what we're going to be seeing and what we have seen in the early months is that school kids are getting infected at a much higher rate than adults are getting infected. And this is part of the reason that the vaccine campaign is directed towards school kids first. But what we also found in looking a little bit closer at the data is that this trend may shift. We went on to ask what happens in the second season, or even in the second wave of transmission in some cases. And we found a reversal, that the rate at which people were becoming infected was higher in adults than in school kids. And we thought, well, why would this be? And thinking about it from a network perspective really helped us. So when you look at a network like our urban network, and you look at how many contacts kids have compared to how many contacts adults have, when this is based on reasonable data, you find that kids have many more contacts typically per day, per week than adults, school-age kids, because they have tons of contacts at school and outside of school, and they're close and they're physical, and compared to adults. And so when a disease first spreads through a population, through a network, it's going to preferentially infect those people with lots of contacts, lots of opportunities for transmission. And if it infects a large fraction of that part of the population, and those people gain some immunity when they're infected, the second time the disease comes through, who's going to be left? Well, it's the people who had fewer contacts in the first place, who are less likely to become infected in the first season. So it's very intuitive that what you would see is the most connected part of your population, the kids, getting infected at a higher rate initially, followed by the adults. And when we did some modeling using these network approaches that I just described, we found that actually we might even begin to see this reversal late in the first season. We may not even have to wait for a second season. So these are model predictions, and these again, blue is the expected infection rate among kids, and red is the expected infection rate among adults. And you see early on that the infection rate in kids exceeds adults, but at some point it sort of equalizes and then shifts. Okay, and so this is important in thinking about what we might expect if we do see another wave in the winter or next fall when we have our next season. And it is also important as we think about how to optimally intervene or control the spread of H1N1. And that brings us to the last sort of step in this process, which is how do we then use these approaches to address public health questions like how do we optimally control the spread of flu or H1N1 flu. And I'm going to tell you sort of the typical approach to this, and then I'm going to give you two very brief examples. So the typical approach is we think about, okay, what kind of intervention do we want to use, and we figure out how to represent that in a network model. All right, and from a network perspective, there are three sort of classes of interventions. The first class of interventions are things we call contact-reducing interventions. So these are things like quarantining people, cohorting sick people, imposing travel restrictions that actually break contacts between individuals and thereby prevent opportunities for transmission. And we can model this by identifying edges in our network that would be broken when we institute the intervention and removing them from the network. And what does that do? Well, it changes the degree distribution in our network, and we can make calculations based on the old degree distribution and the post-intervention degree distribution to say something about how effective that intervention will be at limiting the spread of disease. The second class of interventions are transmission-reducing interventions. So these aren't things that actually change the structure of the network per se, but they reduce the probability of transmission when you do have a contact with someone. So this is like wearing a face mask or doing the elbow bump instead of giving somebody a hug. I think heard of that. Let's find the pointer. Okay, I'll just point with my hands. Or washing your hands, etc. Okay, and so how do we model this? Well, we model this by changing the weights of the edges on our network. We might reduce the weights of some edges and not others, depending on who's going to adhere to the intervention. We get new transmissibility values. We make calculations based on the new transmissibility values, the old transmissibility values. We can make and then compare those calculations to say something about how effective the intervention might be. And the final set of strategies are vaccination. So when you have an effective vaccination and somebody really is immunized by the vaccine, then you remove that individual's node and all their contacts, right? Because they're effectively out of the potential loops of transmission. And so we can identify, let's say we were vaccinating kids in a population, we could identify the nodes that correspond to kids, remove them and their edges from the network, then our network again has a new structure, and we can make calculations based on the network structure before and after to say something about how effective the intervention might be. And so one of the things we've used this approach for in the past and recently is to figure out what our priorities should be in terms of vaccinating individuals. So, and this has been in the news a lot. So who's going to get these first vaccines now that they're becoming available in limited supplies? And one of the important factors that have to go into this calculation, well, there's a couple of important things. One is, what is your outcome measure going to be? Meaning, what is it you're trying to achieve with your vaccination campaign? Are you trying to reduce the number of deaths? Are you trying to reduce the number of hospitalizations? Are you trying to somehow minimize some economic cost? Are you trying to minimize years of life lost? So there's lots of different outcome measures, and we have found that the optimal strategy can very much depend on what kind of outcome measure you use, okay? So I'm not going to talk too much more about that, but I just want you to keep that in mind. The other important input is we need to know what the death rates and hospitalization rates and other impacts of disease are on the different age groups, or the groups we're interested in. This is a graph based on a study that some of our colleagues did at Harvard in collaboration with Public Health in New York City and Milwaukee. They looked at some of the very early data on H1N1 and tried to estimate the death rate, the case fatality rate due to H1N1. It's a very hard thing to do, again, because we don't know the denominator. What we want to know is how many people died divided by how many people got infected. It's very hard to estimate how many people got infected, but there was very good surveillance and early data from both of those cities, and they've done their best with it. And the punchline from that study is basically that overall death rates due to H1N1 are no higher than seasonal flu and much, much lower than 1918. But the age-specific fatality rates are very different in terms of which ages are most at risk. And I would take this particular graph with a slight grain of salt because there's different ways to kind of normalize the data, but the basic take-home message is that in typical years, seasonal flu is most fatal for the oldest age groups and the youngest age groups, and people who have compromising health conditions. And in this case, still the high-risk groups are at high risk, people with health issues, but the baseline for people who are not high risk, the death rates are highest among people between ages 5 and 64, and death rates are quite low for the very young and the very old. So it's almost reversed. So taking into account what we now think we know about the case fatality rates of this disease, what we now think we understand about the progression of this epidemic through the different age groups, that it'll go through kids first and then it'll start getting to adults and other segments of the population, we and others have done analyses using network and other approaches. And basically, without showing you the details, I'm just going to say that what we found is very consistent with the current CDC guidelines, which for the most part, most municipalities are following, although not all. And that's basically first vaccinating those at risk for serious complications and emergency services personnel, so doctors and nurses and others who are going to come in close contact with patients. So these include pregnant women and infants and individuals with chronic pulmonary and other sorts of diseases, et cetera. There's a long list of high-risk groups. And then after targeting those most at risk for complications, we then target those most at risk for catching and spreading diseases, which seems to right now still be school children. However, that may change in the coming months. So if we don't get most of our vaccine until late November or December, and we've really kind of crossed that peak of the wave of transmission, we really might have a different group that's responsible for most of the transmission. And the BARDA and CDC and the agencies that are deciding on these guidelines and distributing the vaccines are in regular communication with our group and other groups, and I think making very making very good and informed decisions as they're going forward. So I'm running out of time. I'm just going to briefly talk about a couple of other things. So one thing we're working on, and I don't want to say too much, is the question of who will adhere. So I mentioned that our NIH grant is really about behavior and perception, and that's really, over the next 5 years, what we're going to be thinking about. So how do people's perceptions and their behaviors impact transmission, impact control? So one of the things we took advantage of, I guess, in the early days of H1N1 was the opportunity to see in real time how people's perceptions were changing, how people's behavior was changing as they got different changing information about this pandemic. And so we launched a survey within 48 hours, and it's still ongoing, and we're actually in the second generation of the survey, basically to find out who's concerned about it, who thinks they're at high risk, who thinks they're at low risk, how that's changing, and who is actually taking steps, going out of their way to avoid travel or particularly early on, avoid social interactions, et cetera. And I'm not going to say much, except I'll say that some very preliminary, don't try to read all this, but some very preliminary findings was that as news tapered off in the early months in June and July, what we found is that people had an increased perceived risk. So as we got late in the summer, people thought, yeah, I guess I am more likely to know someone who's going to get infected, or it is more likely I'll have an outbreak in my community, or I myself will become infected. But at the same time, they became much less interested in and less willing to actually adhere to intervention measures. So they were less interested in going and getting a vaccine when they became available, or less willing to limit their sociological interactions. And the one, I guess, interesting tidbit is that women were actually more concerned and more willing to accept interventions than men were, for what that's worth. Okay, but anyways, that's very preliminary. And as we go forward, as we continue the survey, we're continuing to do it through the fall as we get new information, like Obama just declared a national emergency around flu, where we're getting information that's going to tell us something about how people's perceptions change and how they are influenced by different sources of information. Okay. The last thing I'm going to talk about very briefly is these new methods that I mentioned in the beginning that allow us to do really effective optimization of intervention strategies, okay? And we've applied this to the question of what to do with antivirals. So prior to having vaccines, and with the exception of actually telling people to close schools or limit their interactions, the only other kind of tool public health has had in its toolkit is antivirals, okay, these antiviral medicines. And over the last 5 years, the U.S. government has been building a stockpile of antiviral drugs to be used in just this kind of event. And the goal was to have 50 million antiviral courses stored in the federal strategic national stockpile, and an additional 30 million courses held by the states. And they gave money to the states to buy those 30 million courses, and they gave money proportional to how many people live in each state. So this is what we call pro rata, proportional to how many people live there. Okay, so those were almost all in place prior to the emergence of H1N1. In addition, they gave out 11 million of the 50 million federal courses to the states pro rata. So given that the states hadn't quite bought all their courses beforehand, et cetera, states had about 35 million to use in May, and then the federal stockpile was replenished to 50 million, and the question was that we addressed was how can we optimally use the remaining 50 million, not only to treat people to prevent death, but to slow the spread of disease prior to the availability of vaccines, okay? Now, I will say the CDC has not adopted this policy. There was no effort to use antivirals to slow the spread of disease. So far, the CDC policy has only been to use antivirals to prevent severe illness and death in people who are high risk. So this was a question that was asked of us. How could we use it to slow the spread of disease? But they never really actually took any steps to use the stockpile to slow disease. And I think it was partly because quickly on they perceived that this was not a highly virulent flu and that we should maybe hold on to our antivirals should things get worse for any reason. But this is the question we addressed. How should the federally held portion of the stockpile be deployed geographically, demographically, temporally? And the approach we took is different than the approach that's been used in the past in our field. So in the field of mathematical epidemiology, decision makers and mathematical modelers typically evaluate a relatively small set of options and make decisions based on what our models predict to be the likely effectiveness of each of those options. So vaccinate school kids, vaccinate adults, maybe 50-50. Maybe I'll come up with 20 combinations and run those through my model and see which is most effective. But there have been methods, optimization methods developed in other fields, particularly operations research, that we are able to use that allow us to basically simultaneously evaluate not tens, not hundreds, not thousands, but hundreds of millions of strategies, options in a very short amount of time, within the weeks or months that the public health officials want answers. And we adapted some of these methods, and we used the amazing resources in the Texas Advanced Computing Center that's based at UT that I think that there are some folks at Rice who also use these amazing supercomputers to basically search millions of strategy options at once. And the question we asked was, okay, we have this strategic national stockpile. When should we be giving them out to which cities and in what proportion? So should we be giving them out to cities proportional to how many people live there? Should we be giving them out to cities proportional to how many people are currently infected? Should we hold on to them till the peak of the epidemic? Should we deliver them on a regular basis every week, every month? And so you can imagine there's lots of combinations of schedules you could use to distribute them. And so we searched through lots and lots of these. This is just a movie kind of illustrating what our model does. The circles are the 100 largest cities. You're going to see the fraction of the pie that turns green is how many people are infected. Red lines indicate the travel of infected people between different cities. And there were little purple bars at the very beginning that showed the amount of antiviral stockpiled. So here you can see here, stockpiled at any point in time. And this is a visualization that helps us get some intuition after the fact. Once we've done our search and we find some good strategies, we use these visualizations to try to help understand what's going on. This is not actually part of the optimization itself. And it also really helps us to communicate with public health when we're trying to describe to them what our model is doing and why these strategies are expected to do what they're going to do. So it's been a really great resource and a really great exercise, and will probably allow us to really, this approach will allow us to do much more effective policy analysis in the future. For this particular study, we ran 200 cores in parallel for several weeks. Each core ran about 1 million simulations of disease transmission through the United States per 48 hours. Punchline is what we did in about a month at TAC would have taken me 70 years on my desktop computer, which is a nice desktop computer, which is how I've done all my analysis in the past. And we're soon to release, we're actually developing a optimization platform specifically geared for epidemiological optimization, but that will be freely available to the community. And I'm not going to actually, since I've run out of time, I'm not going to go through what the optimal strategies look like. I'm going to jump right to the conclusions, which summarize the essential points. So the conclusion here is that after doing all this fancy optimization and finding some really complex distribution schedules that would work really well, what we also discovered, fortunately, is that there's a very simple strategy that's expected to work almost as well as any kind of fancier distribution schedule, which is really good, because if we had tried to communicate a very complicated distribution schedule to the feds, they probably would never have adopted it. Not that they've adopted this, but at least this has more chance of making it to the playbook for the next pandemic. So the recommended strategy is a regular release of a small fraction of the stockpile, in this case every month. So it happened to be 5 million courses per month, regardless of uptake. Okay, and uptake is the parameter that tells us how many people, what fraction of H1N1 cases are actually treated with antivirals within 48 hours. At current levels of treatment, so the rate at which people are actually receiving antivirals, which early in the epidemic was less than 20% and is now far, far less than 20% of cases, antivirals, even with this best strategy of this 5 million distribution, they can't do anything to limit the spread of disease. We're just not treating enough people to to really reduce transmission. But they can, and they certainly are being used to save lives. They are being used to treat people who are in high-risk groups or are developing serious disease. And much higher levels of treatment would be required to slow the course of the epidemic. The CDC, like I said earlier, has not opted for that policy, but it is under discussion, even still for H1N1, and it certainly will be under discussion for under what situations for future pandemics should they try to use the stockpile to limit transmission and slow transmission. So finally, by combining traditional mathematical methods with network models and more recently with powerful optimization techniques, we as mathematical modelers can provide valuable decision support for public health policymakers. We don't tell them what to do, but we explain our models, we tell them their limitations, we tell them what they find, and then they take that information and lots of other information and political pressures, et cetera, and they make their decisions, which I think for H1N1 have been pretty good so far. So with that, I just close by acknowledging a long list of people who've worked on these projects with me, and some of the funding sources, including the NIH grant that I described earlier. So thank you very much for your attention. Yes, yeah, and I'd be happy to take questions.
Are there questions? We can do that for maybe 5 minutes, and then we can go out to the reception.
Yes.
I've spent this whole lecture hoping that you have gotten the vaccine.
Oh. Why did you, okay. 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 I'll go ahead and start answering that while you're switching. Okay, let's see, I'll give you this.
Here, just this.
Okay. I ran out of batteries, is that what happened to me?
I'm guessing.
Okay. Can you hear me now? Yeah. Yes. Okay. Okay. I hope you guys could hear me on this. Yes. You could. Okay. So I'm pregnant, as you might see, so I'm a high-risk group, and I'm planning to get the vaccine next week. So why haven't I gotten it yet? Well, it is recommended for pregnant women. I think it's going to be safe, but they're actually in the final weeks of the clinical trials for pregnant women. And so the results should come out any day, and I figured, why not wait 2 days just to be sure it's safe for pregnant women? Yeah. So I intend to get it, and my kids will get it as soon as possible. So, yes?
Why is the disease more dangerous for pregnant women?
That's a good question. So the question was, why is the disease more dangerous for pregnant women? And there are different theories out there, but generally speaking, pregnant women have sort of more depressed immune systems, I think partly because you don't want your immune system to fight your baby, basically. And so they're more vulnerable to sort of serious, more severe disease when they're infected by all sorts of viruses. But for some reason for flu, not just for H1N1, for seasonal flu as well, they're more vulnerable to developing pneumonia and other serious complications. Yeah. Yes?
About the different structure of the human connections, so what degree distribution do you use?
What degree distribution do we use for what? For the
human connection?
for human connections, okay.
Some survey data, which is the degree distribution.
So, okay, so the question is what kind of degree distribution do we use in our models, our network models? And what we try to do is we try to get empirical data and build a network model and then use that empirical data. So it may not be something nice like scale-free or completely homogeneous. It's usually somewhere in between. For the urban network that we've developed based on data from Vancouver, we find that the degree distribution, it's slightly bimodal. It looks more like an exponential degree distribution than a scale-free or a Poisson degree. So it's not very homogeneous. It's not totally homogeneous, but it's not a scale-free distribution. For those of you who you may have heard about it last week or last month in the network, scale-free distribution is a distribution is characteristic of a network that sort of has a hub and spoke structure. So most nodes only have one or very few contacts, but you have these like kind of core hub nodes that have lots and lots of contacts. And we don't find that. That has been found to be the structure of sexual transmission networks for certain high-risk populations, but for respiratory disease networks, based on the data we've used, and there's been now a number of diary and survey-based studies where they actually ask people to walk around for 2 weeks and write down how many people they're coming in contact with. From that kind of data as well, it looks like contact patterns are more homogeneous than a scale-free distribution, but certainly not totally homogeneous as is assumed in these simpler models. Yes?
Yeah, you mentioned that your network models show that what strategy ends up being optimal depends upon your goals, whether it's to minimize the impact on the economy, hospitalizations, deaths, which sounds like a real good goal.
Yeah, I agree. Yeah.
If you elaborate a little more on that.
Okay, so the question was, I mentioned that the optimal strategy may depend on your outcome measure. And so, for example, right now we're in the midst of a study, and so take these results with a grain of salt because we haven't really finished it. But right now we're doing a study of what should we be doing in the next few weeks with our as we roll out the rest of the available vaccines. And we're analyzing two outcome measures. One is reducing hospitalizations, and one is reducing deaths. And I hope I get this right, but I won't even tell you. For one of them, the optimal strategy. For hospitalizations, the optimal strategy is to target the high-risk groups first, so like in the first weeks, followed by the children, followed by the adults. In the reducing death strategy, it's actually the kids first, not even hitting the high-risk groups, and then mixing kind of the adults and the high-risk groups next. And so, I mean, it's sort of a quantitative thing in the end. There's certain groups have higher. You look at their death rates, you look at their hospitalization rates, and so it comes out that as you change that outcome measure, who gets it, who's the optimal target for each week changes slightly, even though overall, still in your first few weeks, just in a different order, you still want to target those three core groups.
Who's the decider?
So the decider is very complicated to me. So the decider is, in the end, Secretary of Health and Human Services Sebelius and Obama to some extent. But the recommendations come through the CDC. So I believe these people get together in Washington. This is all under Health and Human Services. But CDC, the leaders of CDC get together with BARDA, who are the ones with the vaccines who are deploying it, with, when appropriate, the Secretary of Health and Human Services. And together they make a group decision. And the CDC is the one that ends up posting the guidelines. And then these are just guidelines. So local health authorities who actually get vaccines in hand decide locally what they're actually going to do. So this is not a law. I mean, it's not like you have to give them these. And in fact, as I was walking here, I was reading on my little phone an article from like ABC New York or something like that said that New York had been promising that they were going to start a vaccination campaign in the middle schools, and just today decided they're not going to. So it's really left to kind of the individual jurisdictions. That said, it seems in most places what I've heard is that high risk and very young kids are getting priority right now, and then the question is kind of who gets it next. Is it going to be elementary kids, adults? Is it going to be school kids? What it sounds like New York is actually planning to do, according to this very brief read of the news article, is instead of doing the middle school-based vaccination, and instead of targeting high-risk groups as kind of the next round, they're just going to have public vaccine clinics, and anybody can come in and use and get a vaccine. One of the reasons that I read in this article, and who knows, this may change tomorrow, this may not be even true, but one of the things they were concerned about, they said in the article, was that people would come in and say they have asthma, but how are they going to prove they're going to have asthma? So it's really hard to know when you're doing these vaccinations at these clinics where you don't have health records, who's actually high risk and who's not, and so why even bother to try? I mean, that's one particular location, but in the end, it comes down to local decision makers. Yeah.
Looking at the big picture, could you just comment, is within your purview, do you have any data to comment about the risk-benefit ratio of using antivirals with respect to mutations?
Yeah, so this is a really important issue. And so the question is, what about the risk of antiviral resistance? So the more antiviral drugs you use, the more people you medicate, the higher the risk of actually cultivating or selecting for an antiviral resistant strain, and then antivirals are not going to be any good for anyone if that's it. So this is a real concern, and it's something that's been talked about in all the years of pandemic planning. And in all the strains of flu we've seen up until now have eventually acquired antiviral resistance. And so we know it's a real possibility and that it's just a matter of time. If this was a very severe pandemic, a much more virulent disease, I think there would have been a much more proactive use of antivirals early on, and it's one of the reasons that the CDC has held back. That said, UK was using antivirals very liberally for most of the summer and into the early fall. There are other places around the world who've been using antivirals much more liberally than we have. And while we've seen isolated cases of antiviral resistance of H1N1, fortunately we haven't yet seen sustained transmission of an antiviral resistant strain. But you know, the mathematical models basically say it'll happen at some point, but we don't really have a good guess as to how long it will take. And the hope was that in thinking about the next pandemic, when we're really planning for avian flu and assuming the worst case and that we'd want to use antivirals, there was some thought that you want to use them effectively early on to minimize deaths and slow transmission as much as possible before you have a vaccine. But there was some attempt to think about what is the best strategy for using our second line antivirals combined with our first line. And one of the suggestions sort of early or prior to the H1N1 epidemic was perhaps to start out with our second line Influenza and let that kind of do its work, and then at least it buys us a little more time, and then go to our first line, you know, just knowing that eventually we get resistance. So people are certainly thinking about that, but there have been no real hard and fast predictions as to how much time we'd have before they're no longer useful. Yeah. Yes?
Is there any way we can access your notes after?
Oh, sure. They asked me if there's any way they could access my notes after the slides afterwards. Is that what you're asking?
Yeah.
I'd be happy to provide the slides. Yeah.
And this will in fact be posted as a video on the Scientia website in just a couple of weeks. But if you want it sooner than that, Lauren, if you do that, that would be great.
Sure.
If you can give it.
You know, why don't you send me an email and I'd be happy to.
What's your email?
Okay. No, that's fine. Right afterwards, I'll write it down for you. Okay.
Yeah, and that really needs to be our last question, at least because Lauren has to get a taxi at 5:30 to go to the airport. But I do want to thank you, Lauren, very much for a fabulous lecture. As we all await the dreaded third wave. But please do join us outside for the reception, and please also join us on November 10th in the evening when Laszlo Barabazi, who was the co-discoverer of scale-free networks, will be here to deliver the annual Bachner Lecture. Thank you all very much for coming.
This program is protected by copyright and may not be redistributed in whole or in part without the express written consent of Rice University Digital Media Services.